Your long-running tasks shouldn't leave users staring at a spinning wheel with no updates. We'll implement 2 professional-grade patterns for handling extended operations in FastMCP. First, by enforcing strict timeouts to prevent hangs, then by wiring up real-time progress tracking with a custom handler that fires at every milestone. The same call tool method powers both approaches, and you'll see exactly how to plug each one in with minimal code.
Async with client. Hash with timeout. Aborts if execution takes longer than 2 seconds. Result equals await client call tool. Long-running task. Param value. Timeout equals 2, 0. Hash with progress handler to track execution progress. Result equals await client call tool. Long-running task. Param value. Progress handler equals my progress handler.
This demonstrates the enhanced RPC execution pattern with built-in quality of service controls. The pattern extends basic remote procedure calls with first-class support for timeouts and progress tracking, treating them as core execution parameters rather than afterthoughts. What makes this distinctive is the seamless integration of operational constraints into the call signature itself, without requiring separate monitoring systems. The approach works by embedding execution metadata directly into the call contract. Timeouts become part of the invocation semantics, while progress handlers operate as reactive callbacks that don't block the main execution flow. This design maintains clean separation between business logic and operational concerns, allowing tools to focus on their core functionality while the framework manages the execution lifecycle. This pattern matters because it solves the dual problems of reliability and observability in distributed systems. Timeouts prevent cascading failures from hung operations, while progress tracking transforms opaque long-running tasks into observable processes. The trade-off is minimal, just 2 optional parameters, while the payoff is production-grade resilience without requiring external monitoring infrastructure. It's particularly valuable for AI integrations, data processing pipelines, or any scenario where you need to expose backend operations with enterprise-grade controls. Let's break it down line by line.
Async with client.
This establishes an asynchronous context manager for the client connection. It guarantees proper resource cleanup when the block exits, preventing connection leaks. The pattern is essential for managing async resources like network clients.
Hash with timeout. Aborts if execution takes longer than 2 seconds. Result equals await client call tool.
This invokes an AI callable tool with a hard timeout. The 2-second limit prevents indefinite hangs, ensuring the system remains responsive even if the underlying task stalls. Critical for production systems where reliability matters more than partial results.
Long-running task.
This is the tool identifier, specifying which registered FastMCP tool to execute. The string must exactly match the tool's registered name in your @MCP tool decorator, ensuring the client calls the correct backend function.
Param value.
This dictionary defines the tool's input parameters. Each key-value pair maps a parameter name to its value, forming the exact payload the tool expects for execution. This is the standard pattern for passing structured arguments to FastMCP tools.
Timeout equals 2, 0.
The timeout equals 2, 0 parameter enforces a maximum execution duration of 2 seconds. This prevents indefinite hangs when calling external tools, ensuring your application remains responsive. Critical for production systems where reliability matters more than waiting indefinitely. Closing parenthesis terminates the call tool invocation, finalizing either the timeout configuration or progress handler attachment. This ensures the method executes with the specified constraints or callbacks, preventing ambiguous parameter passing. Standard Python syntax for completing function calls with named arguments.
Hash with progress handler to track execution progress. Result equals await client call tool.
This demonstrates the progress tracking pattern for long-running operations. The progress handler parameter accepts a callback function that receives real-time updates during execution, enabling progress bars or logging without blocking the main thread. Critical for UX in Async workflows where users need visibility into operation status.
Long-running task.
This specifies the tool name to execute on the server. All registered FastMCP tools must have unique string identifiers, and this is how the client references them.
Param value.
This dictionary defines the tool's input parameters, mapping parameter names to their values. The structure mirrors the tool's schema, ensuring the AI call provides all required arguments in the expected format.
Progress handler equals my progress handler.
This injects a progress callback for long-running operations. The handler receives periodic updates, enabling progress bars, logging, or cancellation logic, critical for UX when tasks exceed 500 ms. Closing parenthesis terminates the call tool invocation. This finalizes the method call with either the timeout or progress handler configuration, ensuring the client executes the tool with the specified constraints. The pattern demonstrates how FastMCP supports both execution control and real-time monitoring through optional parameters. Advanced execution control. The timeout and progress handler parameters in call tool transform simple tool calls into managed operations, giving clients precise control over long-running tasks without changing server-side logic. Specifying a timeout doesn't guarantee immediate cancellation, as the underlying operation may still complete after the timeout if it doesn't respect cooperative cancellation. Always design progress handlers to be idempotent, as clients may receive duplicate progress updates during network retries.
The operation that never finishes is the only one that never disappoints.